Okay, amazing. Okay, let's start with the easiest thing there is. Okay, can somebody tell me what is 1 plus 2 plus 3 plus all the way up till n? Very easy. Everybody should know.
n into n plus 1 by 2.
Amazing. Wow. Okay. What is 1 plus, sorry, 1 squared plus 2 squared plus 3 squared up till n squared?
n into n plus 1 into 2n plus by 6. 2n plus 1 by 6.
Okay. Can you repeat that for me, please? N into n
n
plus.
plus 1 into 2n plus 1 upon 6.
That sounds slightly more complicated already. Okay, can you guess what my next question is going to be?
1 cube plus 2 cube, I guess.
Amazing. People are mind readers. Okay. Yeah, can somebody tell me what this sum is?
n into n plus 1 by 2 whole square.
Um,
If I remember correctly.
n into n plus 1 by 2 the whole squared. Okay, next question. What's the next question going to be?
Power 4.
Okay, does somebody know the answer to this question?
I believe it's n into n plus 1 into 2n plus 1 into 3n plus 1 by 30 or something like that.
Damn, where are you getting all this from? Okay, so the thing we'll be starting off today is like just trying to look at different ways or really slick ways to evaluate these sums. Okay, so personally, I have a really bad memory. Comes with old age, it's okay. But I'm not able to remember all these things like Moses. So what do? We try to come up with cool tricks to evaluate these sums. Okay, so the usual one that everybody knows for 1 to n is probably just write the same sum in the opposite order and then sum up the things. So every sum is going to be n plus 1. This will be n minus 1. So these two add up to n plus 1, these two add up to n plus 1, and so on and so forth. So when we add all of these, we'll get n times n plus 1, but we divide by 2 because we took twice the sum. This is probably the one everybody usually knows. And now when we move on to summation I squared, the same trick does not work. So how could we possibly derive this? Let's say we don't know this formula and you want to derive it. So there's a very cool way to do this. So okay, firstly, there are so many observations to make here. For example, when I'm summing up m raised to 1, the I2. When I'm summing up, the resulting term has degree 3. When I'm summing up everything raised to 3, the resulting term has degree 4. So that seems like a cool observation that could help us. Okay, so let's get back again to trying to evaluate summation I squared. How do we do that? So I'm not very sure about how to motivate this, but okay, yeah, so since summation I square has something to do with cube, let's try to look at something to do with cubes. For example, if we look at I plus, that is just I cube plus 3I squared, I'm just going to type this out. I cube plus 3I squared plus 3I plus 1. And this is really helpful, I'll tell you why, because now I can take this I cube to the other side and I can just say I I plus 1 cube minus I cube is equal to 3i square plus 3i plus 1. So if I want to write it out, I get to some really nice things. Like, let's say I know 2 cube minus 1 cube is 3 times 1 square plus 3 times 1 plus 1. If I plug in I equal to 2, I get 3 cube minus 2 cube is equal to 3 times 2 squared plus 3 times 2 plus 1. Then I can do the same thing for 4 cube minus 2 cube. And I get that's equal to some expression in, again, something. Can somebody predict the next nice thing to do over there? What should we do with all these equations that we're getting?
Plug them in, then they cancel.
Say that again.
Find the sum in many terms, cancel out.
Exactly. If we just sum all of these, then a lot of things cancel out. So this is also called the telescopic series because this cancels, and so on. Okay, that's a good motivation to take a sum. And what happens to the right-hand side? The right-hand side is also really neat because, okay, let's say we end this at n cube, n plus 1 cube minus n cube, right? So this will get cancelled out with this, and so on and so forth. This gets cancelled out with this. So at the end, the left-hand side is just n plus 1 cube minus 1 cube. And the right-hand side, on the other hand, is also something nice. If we look at all these terms, it's going to give us 3 times summation of all squares. Right? It's going to be 3 summation I squared. This is going to be 3 times summation of all the first degree. So we have 3 times this sum plus 3 times this sum plus all of them raised to 0. Now this is really neat because we can use this to find, let's say we knew that summation I was n into n plus 1 by 2, then we can just plug that in. And let's say you wanted to find summation I squared, then we can just plug in the value of this. We already know this is going to be n. This is going to be n into n plus 1 by 2. And now we get some very neat equations in terms of just n. In terms of just n, we get an equation for summation I squared if we just rearrange the terms. Does this make sense? Yes, no.
Yes.
Okay.
Okay. Yeah, so I personally, when I first saw this trick, I was very blown by it. Just because how neat it is. It might seem unmotivated at first, but if you think about it for a while, it starts to make sense. And now if I want to find, let's say, summation I cubed, then I do the same trick except I cancel fourth powers. So if I want to find summation I cubed, I look at 2 to the 4 minus 1 to the 4. Then I look at 3 to the 4 minus 2 to the 4, and so on and so forth. I evaluate these and sum them up. So on the left hand side, I'll get something like n plus 1 to the 4 minus 1 to the 4 is equal to some equation in terms of summation I cubed, something in terms of summation I squared, something in terms of summation I, and something in terms of summation 1. So this is sort of like an inductive idea. So if you want to find, let's say, summation I cube, if you know the previous summations, you can do that. Yes, exactly. So somebody in the chat is said, so for expressions like 1 to the n plus 2 to the n up till x to the n, we do this for x plus 1 to the n plus 1 minus x to the n plus 1 and continue this process. Amazing. And okay, this was one way to do it. So I won't be actually figuring out the details of the algebra. You can try to do this later. And in fact, there's actually very cool patterns to find here. For example, these summations can also be written as some things as an equation in terms of the binomial coefficients. Like if you know what NCR is, then n into n plus 1 by 2 is just NC2. Sorry, n plus 1 C2. And then this turns out to be something very cool in terms of the terms of some other binomial coefficients. So because there's some really good exploitations that we can do with this. We won't be going into that right now. You can check it. You can go through it later. Okay. I'll assume so far so good. There's another really cool trick to do this, which is not as neat as this one, but I'll mention it anyway. So usually, when we have summation I square, as we saw, that it turns out to be a degree 3 polynomial. When we have summation I cube, it turns out to be a degree 4 polynomial. So we can just assume the coefficients to be some variables. So let's say we want to find summation I to the 4. Then we can just say, we can assume this to be some expression in terms of an to the 5 plus bn to the 4 plus cn cubed and so on and so forth. And now we look at small values of n and plug those in. So let's say when n is equal to 1, we know that all of these, if we plug in n is equal to 1, we know that the left hand side should evaluate to 1. We know that the right hand side should evaluate to a plus b plus c and so on. So we get this. When n is equal to 2, we get something like 32a plus 16b plus something something something. And on the left hand side, we get 16 plus 1, which is 17, is equal to this. So now since we have we have 6 coefficients, we need to look at 6 such equations. In fact, we can also look at 0 is equal to the last variable, whatever it is that we get. And then, so we look at 6 such equations and we get, all of these are linear. We have 6 variables. So we have 6 variables, 6 equations that must have a unique solution. We solve for them using whatever trick that we have learned in school or whatever it is. And we evaluate coefficients in that way. So this is, I feel, a much less neater trick than this one. But just in case you see a similar problem and you need to, you are not able to see how we can do the telescopic argument, you can always just do this. Okay. Easy peasy lemon squeezy. Okay. So these were some nice things. There's another very cool way to evaluate sums, like the different type of sums. Let's say we have something like a geometric progression. We all know how to do that. Let's just quickly brush upon it. So let's say we have Sn is equal to something like r plus r square plus r cube up until r to the n. So how do we figure out what this sum is? Also, like just in general, the notation is, this is a sum, but this is not something that is a closed form, because we have to do things step by step and add those things in that way to calculate Sn. What you're looking for is a closed form, which means if I know n and if I know r, I can just directly plug it into some equation and directly get the answer. So how do we find the closed form of Sn? Have people seen this before?
It's r power n minus 1 upon r minus 1.
Yeah, and the way to derive that is just multiply this by r, and you just see that the sequence shifts to the right by 1. So this is just r square plus r cube up until r to the n and then r to the n plus 1. And now you can just subtract both of these because they have a lot of things in common. And we get Sn is equal to r to the n plus 1 minus r divided by r minus 1. Okay, easy. Yeah, it's a GP. Okay, now let's take it one step further. Let's define, let's say, instead of Sn, we call it Tn to be summation, let's say, 1 times r to the 1 plus 2 times r squared plus 3 times r cubed and so on until n times r to the n. How do we find this sum? Any ideas?
We maybe try to do the same thing like multiply Tn by r and subtract Tn then again. It would be
Yeah,
r
makes sense.
squared plus r cubed.
So if we subtract by r, now we get something like r squared plus 2r cubed up until something something n r to the n plus 1. And now we subtract, and that gives us r plus r squared plus r cubed until some r to the n. And but then there will be a minus n r to the n plus 1 at the end that we need to take care of. And now this is again GP. So we know how to do this. Okay, amazing. I think these were more or less the initial warm-up things I wanted to do. Okay, let's move on to the slightly more fun part. Okay. So okay, we have sort of discussed or used the term polynomial once or twice here and there. So we'll be trying to explore those more and more. So let's say we have a polynomial. Okay, how many of you were there in an NT session earlier that we had? It was a very neat thing that we did over there. Okay, let me just define a few things in case people don't know. So polynomial is just something that looks like this. A polynomial in X, something that looks like this, where n is an integer, non-zero. N is also known as the degree, and these are all an minus 1 are all called the coefficients, and an is known as the leading coefficients, a leading coefficient, and a number alpha is said to be the root of polynomial p if p of alpha is equal to 0. So a very cool fact. Okay, how do I want to say this? Right. So a really good property that we discussed that was very helpful to us in our previous NT class was the Euclidean algorithm that holds for numbers, right? We know that, sorry, Euclidean algorithm, what's it called? Euclidean theorem. I forgot what it's called. If you have numbers a and b, then there exist unique numbers, integers a and b. Then there exist unique integers q and r such that a is bq plus r. And there are more conditions like r has to be greater or equal 0 and strictly less than absolute value of b. Okay, this is the Euclidean algorithm. Euclid's lemma, yeah. So a very cool thing also holds. So a very similar thing also holds over here. So now let's try to figure out what it is. Initially, let's just focus on polynomials which have integral coefficients. So that's what we'll be dealing with right now. So let's say all the AI are integers. How do we come up with this notion of, okay, so firstly, how do we add two polynomials? It's easy. If I add two polynomials which have integer coefficients, I'll get another polynomial with integer coefficients because I just add the corresponding coefficients. Subtracting is also easy. Even multiplication is easy. If I multiply two polynomials, let's say take some very easy example, like let's say x plus 3 and x. Then I'll get another polynomial, x squared plus 3x. We have one fundamental operation remaining, division. How do we deal with division in polynomials? With integer coefficients. Let's say we have some polynomial, let's say 5x cubed minus 3x squared. I'm just making this up right now. So 2x minus 4. Let's say this is one polynomial and let's say we want to divide it by another polynomial. Okay, x plus 2. So how will we do that? So how will we find, how will we do that? So let's try to figure this out as we go. So what do we want? We want to, okay, the polynomial we obtain after division.
We try writing x plus 2 cube and try to simplify q and x.
I'm sorry, I can't hear you properly. Can you say that again?
So we try cubing x plus 2 and then try to simplify it with the q and x.
Okay. So we are going to multiply some polynomial to x plus 2 and get p of x. So what should be the degree of that polynomial?
2.
2, exactly. That's because this, if it had a degree more than 2, then the degree of the product would be more than 3. And if it had a degree less than 2, the degree of the product would be less than 3. So it has to be exactly 2. So, okay, also what will be the leading coefficient? That's also very easy to find out. So if I want to get 5x cubed at the end, what should I multiply? So I know that if I multiply x by this thing, I'm going to get the x cubed term. So this is just really easy thing. What should this be? Amazing. And now what should be the coefficient of x? So the way to calculate that is we know that we look at the next term. How do we obtain the x squared term? Either we take a constant here and quadratic here, or we take a first degree from both. So this is going to give us 10x squared. And now this is going to give us something x squared, and you want the result to be minus 3. So we do minus 13. Then similarly, if we have x plus 2, we get minus 26x and something. Now we want this to be 2x. So It's probably something like 28. But then this doesn't work out because 28 times 2 is not minus 4. So we have something that's a remainder, some remainder. So that's probably like 56 minus 60. So this is something that's very similar to what was happening at the integers. And the way to formalize this, okay, can somebody tell how the Euclid's lemma would work with polynomials instead of integers? Let's say we're given two I'll set it up for you. Given two polynomials px and qx. So there exists a unique, there exists unique let's okay, maybe just call them A and B for the sake of there exists unique so help me finish this. What would be a
There exists unique polynomials in px and qx such that ax is equal to bx into px plus qx, and degree of qx is less than px.
yes, that's the important part. So we have ax equal to bx times px plus qx, and that qx is the degree of, so this is just this much is not enough because for the uniqueness we need an extra condition. So we say either q of x is 0, so either q is 0 or the degree of q is less than degree of p. That's what gives the uniqueness condition. So we won't be proving this here right now, but this is very helpful in general. This gives us a very powerful statement, which goes as follows. So if let P be a polynomial. Also, this is not just true just for integer coefficients. This is true for polynomials with real coefficients as well. So say given polynomial P with root A, so that x minus A divides P. What does this mean? So this means if A is a number such that P of A is 0, then we can write P of x as x minus A times something. How do we go about proving this? Is the statement clear?
We can put p of x as p of x minus p of a, and then expand, then we will get common terms. So
Okay, so you're saying we look at this. Is that what you're saying?
yes.
Okay, and now what?
No, like p of x minus p of a. So we'll be like p of is 0. So p of x is equal to p of x minus p of a. And then like both of them would be having the same coefficients, and the last term would be common. So we can take x minus a common from each of the terms, and we'll get a like polynomial remaining.
Oh, so you're using something here. So okay, something that we probably haven't proved yet. So okay, you're saying we look at the expansion of P of x. Okay, that's a nice way. So you're saying let's say P of x is something like an x raised to n, so on and so forth until a naught. And so P of a, okay, let's not call it a, it's fine. maybe not. Let's say the coefficients are Cnx raised to n up till C naught. And then P of A becomes Cn A raised to n up until C naught. So now we subtract of these. We know that their subtraction is still P of x. But then now we get P of x is equal to the Ci comes common. So summation Ci x to the I minus a to the I. But now what Moksha is saying is x to the I minus a to the I is always divisible by x minus a. Somehow we know. So that's why this has to be divisible by x minus a. Right, that's one way to go about it. Do people have any other approaches? Okay, maybe something that doesn't use the fact that x minus a. So I'll be giving a very cool proof of why x minus a divides x to the n minus a to the n using this. So maybe something that does not use that. The hint is, let's call x minus a is also polynomial. Let's call it to be something like q of x. And you want to show q of x times q of x. Right. So we need to show the remainder when we divide p by q is 0. Now we can use the Euclid's lemma and to say, let's say p of x is some polynomial a times q of x. And let's assume for the sake of contradiction that the remainder is not 0. Since the remainder is not 0, it has to have degree less than the degree of x minus a, so it has to be some constant. So far, we haven't really used the fact that p of a is 0. So what should we do? It's a very nice thing to do. It's kind of just ends it.
So we can replace p of x by p of a, then q of 0, then we get q of a, I guess.
Yeah, if we just plug in a into this, we get that p of a is some number, some polynomial times q of a plus some constant, non-zero constant r. But we know this is 0, and we know this is 0 as well. Q of a is just going to be a minus a, this is 0. This is 0, this is 0, we get r. So r has to be 0. So I find this to be a slightly more cleaner way. This also gives us an insight about why exactly this is true. Okay. So we can in fact use this to show that x minus a divides x to the I minus a to the I, simply because what we have actually shown is something much more powerful. Like let's say we know that when let's say something q of x is 0, then p of x is also 0 for all x. Then q must divide q. This can be generalized to this. Right, the same argument. We divide p by q. And then we and then we just look at some x when q of x is 0, and then we get that p has to be the remainder has to be exactly 0. And then we can use this to show very cool things. Like, for example, it directly just finishes y x minus a should divide x to the n minus a to the n. Or something else like x plus a divides x to the n plus a to the n for odd values of n. So forth. Okay. Okay, here's a nice elementary exercise before we move on. Let's say a and b are integers. Show that a minus b divides p of a minus p of b. Also, like one way is to directly just write out the polynomial p and then do it. But this is also a very useful fact that's used a lot in integer poly type questions. So like one way to do it is the Moksh way of doing it. You just write out the polynomial and then subtract and see that every single term is divisible by a minus b. So another way to do it as well. So can somebody just briefly so what? How do we show this?
You can consider ax as bx minus bb and bx as x minus b, and then just do the same.
Yeah. So we know that when a minus b is 0, then pa is equal to pb. So a minus b must divide p of a minus p of b. So like whatever we saw just now just finishes this. Okay. So this is for Q being degree 1. Okay, here's a fun question now. Let's say I have a secret polynomial, could have any coefficients, real, complex, I don't know. And you want to figure out what it is. You can only ask me questions of this form. You can give me a number, let's say 1, and then I'll tell you what my polynomial evaluated at 1 is. So is the setup okay? So I have a secret polynomial, and the goal is to figure out what the polynomial is. And you can ask me questions. You can tell me a number A, and I'll tell you what P of A is. So how can you figure out what my polynomial is? Also, like how many turns do you need? Can you do it in the minimum number of terms? Can you figure out what my polynomial is? Is the question okay? Okay, excellent question. Do we know its degree? Let's only if you know its degree. What if you don't know its degree?
Like if you don't know the degree, like it would be like really big and you could never guess it.
Okay, so many people in the chat. Oh, the question is maybe using graphs we can get something. And you can get many polynomials that satisfy it. People just unmute and answer it. Yeah, so just to clarify, the question is, okay, so people seem to know how to do this if you know what the degree is. How will you do this if you don't know what the degree is? Any ideas? Something in the chat. Okay, if we know the degree, we can ask as many questions as degree and predict polynomial using this identity. Okay, we can at least get the shape of the graph, which we can get in 3 tests. Then maybe try to use a average of numbers at P of 0. Okay, so let's just quickly discuss how we can find out. Let's say you know what the degree is, then how will you find out what the polynomial is? Let's say you know that the degree is 4. Degree affects the curves of the graph of the polynomial, I think. Let's say you know that the degree is 4. And so what are the questions you would want to ask me? And how will you figure out the polynomial from that? Just to quickly recap. Oh God, the class is so quiet. Four questions, okay. What, let's say, okay, ask me 4 questions and I'll tell you the 4 points. And let's see if you can figure it out. Okay, P of 0, let's say. It's 3, let's say. Okay, let's say P of 1 is 7. I would really encourage people to unmute and ask questions. It's really annoying to hear my voice only. Pf minus 1 is, let's say, 4. Okay, now you only have 1 question left. You guys told me you would figure it out in 4 questions. What is the last question you want to ask me? P of 2, log किया जाए. Oh, P of 73801. Damn. That's the last question you want to ask me? Okay. P of 2. Let's say that's -1. Okay, now I won't be giving any more information. How will you figure out what my polynomial is? Hey guys, please unmute and talk to me. Oh no, somebody says you guys need 5 questions. I don't know, you guys told me you would figure it out in 4. So how are you figuring out what the polynomial is? What are you doing? Tell me your secret. Making equations, okay? How? Okay, let's do the stupidest thing ever. Let's say we only have this much information. P of 0 is equal to 3. What's the stupidest guess you can make for what the polynomial is?
P of x equals 3.
Amazing. So P of x is equal to 3 for all x. But hang on, let's say we have gotten more information. That P of 1 is equal to 7. Now we need to do something clever. So what I'm trying to do here is trying to come up with some kind of a process or like a way by which whenever we get more information, we can just sort of update our stupidest polynomial so that it kind of matches with what all we have so far.
So it could be P of x is equal to 4x plus 3.
Amazing. So maybe P of x is 4x plus 3. Okay, now we have more information about P of -1. How do we incorporate that? Now, what's the stupidest polynomial we can get? And let's try to be more clever about it. So we already know that 4x plus 3 satisfies both of these. So let's say you have another polynomial that also satisfies both of these. Then there'll be something very cool about it. So let's try to be more clever while updating our polynomial. Okay, so somehow we want to use, yeah.
2x squared plus 2x plus 3.
Okay, so that's fine, but I'm not sure where you're getting it from. So that's amazing. But uh, can we come up with like a nice insight, like a nice? We've done some nice things today, some more nice things. Like, how will you come up with 2x² plus 2x plus 3? Okay, one way to do it is just like assume P of x to be some ax cube plus bx squared plus cx plus d and then plug in and then solve the equations. But yeah, I don't want to do that.
Like we could do this, we could like plug in -1 and 4x plus 3 and then see like how much till we get 4 and add that.
Okay.
I
Yeah,
don't know, it's stupid
that's
maybe.
so we already have 4x plus 3 and can we somehow add something to it to incorporate for f -1 being 4?
We can increase the degree.
Say that again. Okay, one person at a time. What did you say?
We can increase the degree.
Yeah. We want to increase. So we will have to, in fact, increase the degree because now we have 3 points, and uh, now if you want this unique solution, like with these 3 points, if you want a polynomial, it has to be at least degree 2. Why is that? Because degree 2 polynomials have 3 coefficients, that's 3 unknowns. And these are like 3 equations. So that's why we have to increase the degree every time a new set of information comes in. Bro, I knew it. What did you know? We will need 5. Oh, okay. We're too late. You guys owe me a chocolate now. Anyways, so we have this. So extending on Saranya's idea, maybe we can have 4x plus 3 plus some quantity. And it will be really nice if this quantity is just 0 when x is equal to 1 and x is equal to 0, right? Because we already know 4x plus 3 satisfies the conditions for 0 and 1. So when we plug in 0 and 1, let's say we get this part to be 0, it cancels out, and then this works out nice. Right? Does that make sense? It's a very important step. So what do we want to do? We want this part of the equation to be 0 when when x is equal to 0 or 1, so that all we have remaining with is this, which we know already works. Right? So how do we ensure that this part is 0 when x is 0 or 1?
Maybe the coefficients, like we are adding two things, so the coefficients should sum up to 0.
Really? Should they? Okay. True. So there's like a quicker way to do this. X into x minus 1, exactly. If you look at x into x minus 1, so we want p of 0 to be 0. Like this thing has to be 0 when x is 0, so x has to be a factor. It has to be 0 when we plug in 1, so x minus 1 has to be a factor. Simply because of the Euclidean algorithm argument that we saw earlier. So this part has to look something like x into x minus 1 times some constant k. Right? And now all we do is we just solve for k. So we plug in x is equal to minus 1 and then solve for k. So we know p of minus 1 is 4. So we get this. Then this becomes minus 1 times minus 2, which is 2k minus 4 plus 3 is minus 1. I think I might have done some calculation mistake here. And then we get k is 5 by 2. So now the updated value of the polynomial is just 5 by 2 x minus 1 plus 4x plus 3. And now, so is this okay with everybody? Okay. If you have any questions, just feel free to unmute and ask. Now we have another value. So just to make sure that everybody's fine with this. Now we have p of 2 equal to something, equal to minus 1. So how do we incorporate for that onto our existing polynomial? So again, we already have a polynomial that works for 0, 1, and minus 1. Right? So we can just copy paste it over here. So 5 by 2 x into x minus 1 plus 4x plus 3. And now we have we want to add something more over here. So what should we do? Yeah, go ahead. Yeah, so we already have something that works for 0, 1, minus 1. So we want this quantity to be 0 when we plug in 0, 1, and minus 1. Which means that x into x minus 1 into x plus 1 divides this quantity. And then we do this and then we multiply it by some k. And then add it up. We get this. And now again we plug in for 2 and then solve for the value of 2.
Say, could you repeat what just happened in the last seconds? Like I was kicked out of the meeting. I don't know.
Sorry, what do you want me to repeat?
Last 20 seconds.
Okay, you didn't miss much. We just saw how to go from, let's say, we knew how to add the information about f2 equal to minus 1. And we already have a polynomial that works for 0, 1, and minus 1, which is this. Now we want to add something to it, and that should be equal to 0 when x is 0, 1, and minus 1. So when does that happen? So x must be a factor, whether it's for polynomials the proof that we saw. If something is a root, then x minus that thing has to divide the polynomial. So we know this x has to divide this, x minus 1 has to divide this, and x plus 1 has to divide this. So it is of the form k times x minus 1 times x plus 1 plus the previous polynomial that we had. And now this we know has to be equal to so now we have this only one variable k, and we plug in x is equal to 2. And we know we should get minus 1, and then we evaluate the value of k. So that this is equal to minus 1 for x is equal to 2. Does that make sense, Sharanya?
Yeah, yes.
Okay. Amazing. And then we continue doing this. And now if you observe this, this is a degree 3 polynomial that we get. And in fact, we can extend this to any degree polynomial that we want by just adding, let's say, the factor of x minus 2, x plus 1, x minus 1, and x, then multiplying it by any polynomial we want, plus this. So so now if we want to find another polynomial, what you'll do is just have x minus 2 times x plus 1, x minus 1, x times, instead of taking any k, we can just set it to be any polynomial, k of x, let's say. And so there are infinitely many polynomials. Okay, let's say maybe, okay, since we had degree 4 to begin with, I can just set it to be this plus this quantity plus this quantity. And now this I get to be a degree 4 polynomial, and I can set k to be anything I want, and 4 of these conditions will be satisfied. So in fact, there are infinitely many polynomials of degree 4, but satisfy 4 of these conditions. So just 4 points are not enough to figure out what the polynomial is. So we always need the degree plus 1 number of points. Is that okay? I hope that's okay. And that can also be seen just by looking at the coefficients as the variables we're trying to solve for. So since there are n plus 1 coefficients, we need n plus 1 equations. That's why we need at least n plus 1 points. Okay, and this in fact is a very fancy thing. So we can generalize this directly, and then that leads to something called Lagrange interpolation. And how does that work? Let's say we know that f of it's basically just the same thing, but a fancier way to write it. So let's say we know that the way to generalize this is, let's say we know f of x naught is equal to y naught, f of x1 is equal to y1, and so on and so forth. F of xi is equal to yi for some finitely many points. Then we can find a degree n, so we can find a degree n-1 polynomial which fits all of these directly by plugging in the formula. So maybe I leave it as an exercise to try and figure out what the actual formula is. It actually ends up looking really. So you don't necessarily have to find the coefficients in terms of xi and yi. You can just leave them like that. Okay. Okay, there's two things we can do from here. Either we can try to solve this question for when we don't know what the degree is, or we can just see some more random things about polynomials. What do you guys want to do? Maybe this question without knowing the degree can be left as homework. It's a really neat question. And in fact, always figure out, let's say if the coefficients are given to be positive, a very cool problem is to figure out what the polynomial is in 2 questions only. Which is a very cool question. Okay. Okay, I'm not sure why people are surprised. Yes, irrespective of degree. Exactly. That's very cool, right? Irrespective of what the degree is, you can find the polynomial and just how to do it. I won't be telling you that, obviously. You have to figure it out. It's not a very straightforward argument. No. You can try it for a while, and if you don't get it, then you can reach out, and I'd be happy to help. Okay. Okay, makes sense. So, okay, some more fundamental facts, like fundamental. Okay, so polynomials, so there's a very cool way to derive the number systems using polynomials. So the legend goes that initially we only had natural numbers, and then we tried to look at polynomials with natural numbers as coefficients. So let's say x minus 2 is 3, then x is 5, all is good. But what happens if I say x plus 2 is 2? This is not soluble in natural numbers. So we introduce the notion of 0 as such a number, and that's how we got whole numbers. I don't know what the notation for whole numbers is. Then people were okay for a couple of years, and then somebody just woke up and thought, hey, what about this question? X plus 5 is equal to 0. All of these coefficients are whole numbers, but the answer is not a whole number. So we define some new number so that x is minus 5 and so on, and now we had integers. So all was well for a few years until again somebody woke up and tried to solve this polynomial. And okay, this does not seem to have solutions in integers. So multiplicative inverses were defined, and then we moved on to Q. Now what happened? Okay, all was well for a few years until somebody just dreamed of this polynomial x square minus 2 equal to 0. Hey, nobody knows how to solve this. So people are like, okay, this does not have a solution in reals. Rationals. Let's make up numbers so that it does have a solution. And those were called real numbers. So now we add root 2 and other things. Actually, these are not real numbers. These are something else. But let's not go into that. But that's the general idea. So numbers which are roots of polynomials with integer coefficients are called algebraic numbers. Sorry, with rational coefficients are called algebraic numbers. So, for example, you cannot write pi as a root of any polynomial with rational coefficients. And that's a discussion for another day. Yeah, not okay. That's no, even root 2 is transcendental, right? But it does have a polynomial for which it's a root. Right. Yeah, no worries. Okay, so now we had that. And then again, for a couple of years, people were really happy until somebody dreamed of this polynomial. And now people were sad again, but not for long because that's what we do. We make up numbers when we don't know how to solve a polynomial. So now again, we solve this and we call this number as I to be the square root of minus 1. Okay, so now we have complex numbers introduced. The question is, can we have something, are complex numbers enough? What do I mean by that? Like, if we look at polynomials with complex coefficients, will all the roots be complex still? Something in the chat. Mathematicians invented imaginary numbers instead of admitting they were wrong. That's an interesting statement. Okay. I am assuming that's a joke. But yeah, so like if you think about it, like every such extension was just invention of numbers. Like I feel like like zyada se zyada, like max to max, maybe we can make out some meaning of, let's say, up to until rational numbers, but that we use in day-to-day life. But when we go to even real numbers, like root 2 is still like very artificial, just like how I is artificial. It just feels like I just feels more artificial because maybe because it's introduced later, or I don't know, it just yeah. But my point being, like, I is just as artificial as root 2 is. Okay. So, and now once we hit complex numbers, people were happy for a while. And okay, not really, right? Complex polynomials can have real roots, perhaps. Sure. So when I say complex, it means real numbers are also complex. So like all natural numbers are also integers, all integers are also rationals, all rationals are also reals, and all reals are also complex. So now the question is, is there something beyond complex numbers that we have to, like, does this chain go on forever or does it stop at some point or what? Yes, 3D numbers. Amazing. What are 3D numbers? Quaternions. Oh my god, all these fancy words. But yeah, so to answer this question, in fact, yes. Okay, what do you think the answer to this question is? Are all polynomials with complex coefficients have all roots being complex? Or is there a polynomial somewhere in this universe which has complex coefficients but does not have complex roots? Wait, you just said yes. Yes to which question? Second. Okay, so you think there is a polynomial somewhere with complex coefficients which does not have complex roots. But as it turns out, it's like again very cool and extremely non-trivial to prove that in fact it does stop at complex numbers. So every polynomial with complex coefficients does have all roots to be complex. And that's in fact also known as the fundamental theorem of complex numbers. I think. Hopefully that's the right term. Right? Indeed, it says yes. Which I think is very cool. Like, okay, why did we just randomly decide? Why did it just randomly decide to stop at complex numbers? Feels pretty unintuitive. But it is indeed true. But some mathematicians are like, it's okay. What if polynomials aren't helping us invent new numbers? We will still invent new numbers by ourselves. And that is something that somebody mentioned about quaternions or something in the chat. So in fact, the mathematicians just still continued to make up new numbers. And in fact, so maybe I won't go too much into it, but quaternions is when so usually when you're looking at a degree 2 polynomial, it has at most 2 roots. That's also a good exercise. Show that in complex numbers or like complex coefficients. That's what I mean. If we a degree n polynomial has at most n roots. Can have at most n roots. And this is not very hard to show. But in fact, so some people were just like, okay, what if we consider a polynomial and let it have more than the degree number of roots? And that's how quaternions came into picture. So quaternions is basically just saying, okay, let's say I is the root of -1 and minus I is the root of -1. But let's also say j and k are roots of -1. And let's see what happens. And people actually defined the system in this way. And the very like mind-blowing fact is like this doesn't even have commutativity. Like over here, ij is not the same as ji. So it's a very, very interesting system to study. So you can look this up more later. But it seems like something from quantum physics. Yeah, like I think there are applications in quantum, but this is like the way I've studied is mostly just abstract without any applications. This is like something that's very cool. But isn't a polynomial having n plus roots called an identity? Yeah, so if you're working just in complex numbers, and if you have, so because of this, if you're working just in complex numbers, you're not going past complex numbers, then definitely, if you somehow get a polynomial which has degree n, so this is a very nice technique that is used. So you have a polynomial with complex coefficients or real coefficients, and you know that its degree is n, and you show that there are n plus 1 numbers for which it maps to 0. Then that just tells you that it has to be 0 on every single point because it cannot have more than n roots. That's in fact a very useful technique that's used a lot solving all types of problems. But what we are doing here is we're going beyond complex numbers and constructing a new world where a polynomial may not necessarily have just a degree number of roots. So you don't have to worry, like this is just for fun and it's not something that will come up in olympiads or anything. It's just like when I learned it, I was very baffled and perplexed and intrigued by this. So you might want to look this up. Will there be a recording of this class? Yeah, there'll be a recording. It's getting recorded, it will be put up on YouTube. Okay. Yeah, like if this part was not okay, don't worry too much about it. Like if the quaternions part was not okay, don't worry too much about it. The important part is this statement. If we have a complex number, so degree and polynomial has at most 10 roots. If this statement is fine, then it's fine, we can move on to something else. You can look up about quaternions. Okay. So in fact, there are some more cool things we can do with this. So let's say now we are looking at a polynomial with just real coefficients. Let's say, so there are some cool things we can do using this. So what will the roots of that polynomial look like in complex numbers? So let's say, say we have a polynomial with real coefficients. What do the roots look like in complex numbers? So we allow the roots to be complex. So what will the roots look like? But the coefficients are all real. So for example, if we have something like x squared minus 5x plus 10. Now this has some two complex numbers as its root. Exactly. Conjugate roots. Amazing. So what is a conjugate? First of all, a complex number looks something like a plus bi. Okay, before we move to this, for people who are seeing this for the first time, show that the sum, product, division, and subtraction of two complex numbers is complex. But yeah, anyways, so we come back to this. So a plus b, if we have a complex number a plus bi, the conjugate of a plus bi is said to be a minus bi. And why is this nice? This is nice because when we multiply these two things, we get a real number. So when we multiply a plus bi by a minus bi, we get a squared plus b squared, which is real because a and b are real. It's called the conjugate. So when we have, so again, this is a nice exercise that if we have a polynomial with real coefficients, then if a complex number is the root of the polynomial, then the what's it called? Conjugate is also a root. So if the starting polynomial is real. And that's also not too hard to show in the end. Just leave it as an exercise. There'll be something going on in the chat. Then division isn't closed. Oh, it is closed. Why would it not be closed? Okay, again, division by 0 is always undefined. Unless you want to be more ambitious and just define division by 0 somehow so that the world doesn't collapse. So that's what mathematicians have tried to do: define new numbers which are previously undefined, make sure the world doesn't collapse. Okay, so we have this, and this gives us really nice things. For example, it tells us that since the complex roots always appear in pairs, any polynomial with real coefficients and or degree has at least one real root. Okay. Kind of. Right. All right. So, yeah, yes. I think I forgot about weird tasks that we were going to discuss. That was promised. Okay, let's do that before we end. What happens when there are complex coefficients? When there are complex coefficients, you can't really comment. So most of the time, you're interested in knowing, at least in Olympiad type problems, you're interested in knowing whether the roots are real or not. And that's why I talked about this result. But when you have complex coefficients, you can't really say much about whether the roots are real or not. Obviously, by the fundamental theorem, you know that all the roots are going to be complex, but you can't really say much about the roots being real or not. Okay, let's end with Vietas. Let's say we are given some polynomial with roots, let's say alpha 1, alpha 2, x minus alpha 1, x minus alpha 2, dot 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 x minus alpha n. And let's say this is equal to x to the n plus some coefficient capital A n minus 1 x to the n minus 1, and so on and so forth. Now, the question that we want to answer is, what is the relationship between the coefficients of this polynomial and the roots of this polynomial? So let's say this is A0. So this is sort of bashy type, but let's just go through it anyway because it's very helpful. Firstly, what is the constant term going to be? The only way to get a constant term is, Vieta stuff, is if we multiply all of these constant terms. And that's just going to give us minus 1 raised to n times product of all the alphas. Right? So far, so good? Okay. And now, how do we get the coefficient of x raised to 1? So we look at what are the different ways to get x raised to 1. So basically, what is multiplication? A very intuitive way to look at like this algebraic sort of multiplication is we take one number from each bracket and multiply it and sum over all of these things. So now if you want to get the coefficient of x raised to 1, what are the different ways to get that? So either we take x from this bracket and all the constants from the other brackets. Or we can take x from this bracket and all the constants from the other brackets. And so on and so forth. Right? So what does that give us? That just tells us that the next thing, so if we take x and everything else in that bracket, that's just going to give us alpha 2 dot 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 alpha n minus 1 raised to n minus 1. And then if we take x from this and alpha is from the remaining, so we skip alpha 2. So we get alpha 1, alpha 3 up till alpha n times minus 1 to the n minus 1. And so on. So we sum over all of these. So this can be written as summation. So basically these are sum of all n minus 1 things. Like summation product of n minus 1 these things. N minus 1 is. So very bad notation, but I hope you see what I'm trying to say. And times minus 1 raised to n minus 1. Now, if we want to get x square, what are the different ways to get x square? So the only ways to get x square is if we take x from some two brackets and the alpha is from the remaining ones. The coefficient of x square is going to be, you take n minus 2 alpha i's at a time and sum them up. And then you take n minus 1 alpha i's at a time n minus 2 alpha is at the time, take their product and sum all such products. That's going to be the coefficient of x square, and so on and so forth. The coefficient, if you want to find the coefficient of x raised to I, what Vieta's basically tells you to do is take product of alpha j for n minus I number of j's, n minus I j's. Take n minus 1 alpha i's product, take their product and sum over all of these things. That will give you the coefficient of this thing, x to the I. These are also known as symmetric polynomials. And there are some very cool things you can do with them also. So this is called the n minus I symmetric polynomial. Okay. Yeah. And there's a very cool result. Okay, some side tracking again. But any symmetric polynomial. So what does a symmetric polynomial mean? Basically, symmetric polynomial is just a polynomial with more than one variable. Let's say x1 to xn. This polynomial is called symmetric if the order in which you take the xi doesn't matter. So p of x1 to xn is the same as p of, let's say, if you instead do x2, x3, x5, you just switch up these orders, just permute the orders, you'll always get the same polynomial. Then that such a polynomial is called a symmetric polynomial. And if you observe all of these polynomials that we get as coefficients are symmetric, and in fact, these are known as the fundamental symmetric polynomials. Exactly. Any symmetric polynomial can be written as a polynomial of the fundamental symmetric polynomials. So again, we can have one entire class about symmetric polynomials sometime. Okay. So that was about VFS. Yes, very good stuff indeed. Maybe we can do a question using VFS. So let's say, and then end over there. Let's say p of x is given to be x to the n plus an minus 1 x to the n minus 1, and so on until a1x plus 1. You know that all of the roots, wait, again, this doesn't really use as that much. So we know that all of the roots are real and the AIs are all non-negative. So all the AIs are non-negative. And we also know that Px has n real roots. Show that P of 2 is at least 3 raised to n. Any ideas? Okay, a quick poll. Do people want to discuss this right now? What if all the AIs are zeros? Okay, my bad. Let's make it strictly greater than 0. Good one. Okay, do people want to discuss this right now? Take it up as a problem in the P side. I like how Mox is always like, when I ask 2 questions and Mox always answers yes. I'm like, okay. He's just like, okay, take whichever answer you want. Okay, you'll do it on your own. Don't discuss. Okay, that sounds good. So if there are no more questions, we can stop here.